Hello everyone. Good evening. Yes, welcome to the session. Today we are going to discuss about this data modeling technique called star or snowflake schema. This is you can also call as star or snowflake model. This helps you in like organizing your data warehouse. In today's world, data warehouses play crucial part in analytics, and all the data, semi-structured data, structured data, like sales data, transactional data, organizations save in data warehouse. And as a data engineer, if you are someone working with data warehouse, your job is not just bringing data to data warehouse, it is all about organizing also. That organizing part we call data modeling, and there are different models which helps you to organize your data warehouses. As name itself says, data warehouses, which means they are like godowns of data. Without proper organizing, they might create chaos. Your end users who are analytic people and who use BI tools to generate reports, they might struggle a lot to query the database. Query might take longer period of times if data is not organized well in your data warehouses. And how to get started, how to learn how we can organize our data warehouse. Yes, for that you should know some data modeling concepts. And in data modeling concept, one of the concept is star or snowflake schema. Star versus snowflake, that means there are some small differences. Rather than that, we can say star or snowflake schema, because the underlying concept is same for both star and snowflake schema. We will discuss about that. Star schema. Star schema is the simplest and most widely used data warehouse schema. In the star schema, you will put facts table in the middle and dimension table. You will split and create relation between the facts table and dimension table. Okay, let me give you an example. Let us take retail chain analytics. There is a retail chain. Let us say they have offline stores as well as online stores. And they want to analyze some insights like what is total sales by region. There is offline data, online data. They want to know the region wise sales, overall sales, total sales by region. Which product categories performs best, like top performing categories, and top customers, these kind of questions, business questions. And to run that analytical code which answers these questions, or to create reports which answer these questions, first we need to extract data. And yes, every day from OLTP system, every hour or every day on some schedule, we are getting data from offline stores, and also we are getting data from online stores. And this data we will provide in data warehouse. Why in data warehouse? They are good for analytics. We are also calling them as OLAP system, online analytical processing systems, whereas databases as OLTP systems. They are good for transactions, daily transactions like inserts, updates. And data warehouses are good for analysis, for running queries like this. The query which gives results, which helps to like sort out sales by region. So these are like compute intensive queries when compared with transaction queries, regular inserts and updates. That is why we use data warehouses. Now in this scenario, we are bringing all the data from OLTP to OLAP system, which is our data warehouse. It's good. And here we need to perform our analysis. And this is going to be the point for the end users, like people who generate reports. They need to query and get data from here. And if this place is not organized well, what happens? You have offline table, you have online table, and daily you are incrementing this offline table and online table. Let us say the stats are like this, not stats, sorry, column names are like this. Sale ID is there, and then sale date is there, product name is there, product category is there, customer name who purchased, their city, state, quantity, unit price. These are our columns, both in offline store and online store. Now every day we are moving this data to offline table, and every day we are moving and adding data in online table. Seems good up to this point, but over the period of time, what happens? They'll become humongous. If you don't organize them well, querying this data might take longer period of time. Can I split the data? That also you can do based on timestamp or based on region wise. You can partition your data. That can improve your query performance. And one more way of organizing your data to improve the query performance, what we can do is we can do data modeling. So in the data modeling, what are you doing? You are splitting facts and dimensions. So facts are like quantity, unit price, and total amount. These are facts. Whenever customer purchases in offline or online, these are the facts. How much of quantity they are purchasing, and what is like unit price for that product, and total amount. You put that facts in center. Center in the sense you separate the facts first, and then you separate dimensions. So for every transaction, I'll be adding the same dimension, same product name, same category. Let us say some 10,000 rows are there that are related to fashion category in the sales table. If you separate this dimension category, you need not like populate 10,000 times the category details. Product name, you need not populate 10,000 times. Further, customer name, that customer has made some 1,000 transactions so far. For 1,000 transactions, you need not like give all the customer details like customer name, customer ID, customer phone number, email, address. All these dimensions are not required to maintain them in one big table. That makes the table heavy. And further querying that table gives late responses because of it's having so much of data. Scans take longer period of time. That means they are consuming more compute power, which will reflect in bill also. And also storage wise, for dimension, let us say something like customer address. Whatever dimensions that are valid, you have to maintain. But dimensions like customer address, if you are maintaining in the sales table, unnecessarily you are populating customer address 10,000 times. That customer has made 10,000 times transactions. 10,000 times you have to write the customer address, which increases storage cost. Further, when queried, which increases the compute cost. And this is not great idea for all the scenarios. For some scenarios, they might be good, but in most of the scenarios, maintaining everything in one big table is not a practical idea. And again, depending from use case to use case, you have to choose your priority. You have to choose the model. Sometimes keeping everything in one table will act as like a single point of truth. Sometimes may not be. In this scenario, for retail sales data, which we are collecting for further analysis, maintaining everything in one table is not needed. For better performance of your data warehouse, you can organize your data well into facts and dimensions by splitting data into facts and dimensions. Now here what I'll do in star schema, I'll create a fact table first, or I'll separate dimensions. I have product dimension, so I'll create dimension product. And product name, first let us put product ID in front of it. This is going to be the primary key for this table. And all the dimensions, like they won't be, most of the times like product name, product ID, all this will be unique columns. You are separating the dimensions. Product ID, product name, product category, let's say product SKU, product brand. This is your product table. You are separating it. For each product, you have one row here. That is one dimension you have split it. And another dimension is store. Store ID, store name, store location, store type, online or offline. These are like store dimension table. Vendor dimension also you can create like dimension store. Now dimension vendor. Same thing, vendor ID, vendor name, vendor location, vendor rating. So these kind of stuff you will save as dimensions. If there are any other dimensions, you will accordingly split the dimension tables. Now facts. What are facts here? Quantity that has been ordered, and like unit price, total cost or revenue, or let's say total cost. These are facts, measures. These are dimensions. Now I'll split facts and dimensions. But saving only quantity, unit price and total cost doesn't make any sense. So you'll create relations. You'll maintain few dimensions along with facts to establish relation with dimension table. For example, product ID I'll have. Instead of having product ID, category, product brand, product SKU, product name, everything, I'll just use product ID only. Same thing, instead of managing the vendor ID, vendor name, vendor location, everything in one big table, I'll just put vendor ID here. And here also store ID. Let me put it over here. Store ID. Now I have store ID, vendor ID, product ID, quantity, unit, and total cost. These are actual facts. Measures, numerical data. Dimensions. The dimension data which are like category data, categories data. And this data will not be changing also very often like these fact data. Slowly they might change. There might be in future, after very long period of time, there might be change in store name or product name. Okay, then we can track the changes and update the tables. Now for every transaction, if I save all these details in one big table, it increases the storage costs, compute costs and everything. So let us plan in this way, facts separate and dimensions separate. And also further we will establish relations. I have store ID. Using store ID, I'll establish relation with store. Using store ID as foreign key. In dimension, with the dimension vendor, I'll use vendor ID and establish a relation between these two tables. Same thing with this. For product, I have product ID in fact table. I'll use that product ID and establish relation. So now when really those insights are required by end users, when they are analyzing those requirements, what they'll do, they'll merge the fact table with the dimension table. They want to know which products are in top by region. Now further you have a region dimension. Now fact plus region plus dimension product. So by merging these, already you have created relation, let's say region ID or region code. By merging this, the end users will make use of data, right? And query performance will increase despite writing a query might become a bit complex because of merging data every time, understanding the relations, using the relations, joining the data, merging the data. So the querying part, query script might be little complex, but response will be faster. And also you are optimizing storage by splitting dimensions. Hardly like say there are 1,000 rows in let's say some 150 rows in region, some 10,000 rows in product, and some 5,000 rows in vendor. That means 5,000 vendors are there, 10,000 products are there, 150 regions are there. If you maintain everything in one big table, the same data you will be writing into the fact table some millions of times. That is the advantage with star schema, separating facts and dimensions. Right, denormalized structures, you're splitting the data, simple joins. You require only single join between fact and dimension. Fast query performance and easy to understand because of the structure. It's easy. Dimensions are separate, facts are dimension separate. Sorry. Higher storage requirements, data redundancy. Like it doesn't increase your storage requirement because you are separating. Small correction is needed here. For retail analytics, for financial reporting, for these kind of use cases, you can choose star schema. And further, if you split your tables into more detail, then it is Snowflake schema. See, Snowflake schema is something like this. You have facts, dimensions, and subdimensions. For the same example, retail analytics, you will maintain facts table anyways, and you will create dimension product table, dimension vendor table, dimension store table, dimension region table. Now if you split these dimensions into further details, like in dimension product, further you split data product category, detail product categories, and detail subregions. I mean locations. In dimension region, you will only maintain city names. In the subregions table, you are also maintaining the areas in that way. Same way here, product category details in more detail. Dimension vendor. If it is required for dimension vendor, we will create another dimension table. You're splitting the dimensions basically. Further store details, you are splitting it. on some basis. Then it is Snowflake schema. That is star and Snowflake schema. Comparatively, star schemas are simple than Snowflake schema because of having sub-dimensions. It will become like a little bit complex to design. Star are faster. Snowflake is slower because of multiple joins. Storage efficiency, it is higher, and comparatively it is bit lower here. Data redundancy high, here it is minimal. So comparatively, star schema is best for most of the models. In some scenarios, if you have too many dimensions, like regions and areas, you are saving location data. And you want to save your location data like in pinpoint area wise. You have country, and then you have state, and then within that you have cities. In the cities, you have areas. When you have too many dimensions like this, you can plan Snowflake schema. Otherwise, star schema is more simpler. Yes, I'll take to some examples to understand star and Snowflake schema in better way. An online retailer needs real-time sales analytics. The example which I took earlier also. Then star schema is best thing here. Star schema with sales fact table and product dimension table, customer, time, store dimensions. It is better to maintain separately. Easy to query, and query response will be quick. You are also optimizing storage and compute. These are the advantages rather than maintaining everything in tables like that. Now, Snowflake schema, in which scenarios it is better? A global company tracks products across 50 plus countries with complex organizational hierarchy, like country, region, city, and within the city, other things, areas, and product category, subcategory, products like this. If you take an example of e-commerce site, also same thing, right? Today's e-commerce site, they need to maintain like a location table. The location table should have worldwide countries, regions, cities, areas. Maintaining everything in one table will become humongous. So what they can do, they can create countries as one table, and they split another table, regions, and create a relation between country table and region table based on country ID or country name. And further regions can be like a country and then city and then region is better. Anyways, like this you can create sub-dimension tables. It is good when you have a complex dimension hierarchy. In such scenarios, Snowflake is good. Financial institution. A bank needs both fast transaction reporting and detailed hierarchical analysis. They can implement both. Star schema for frequently queried dimensions and Snowflake schema for complex dimensions, like account hierarchy, branch structure, in this way. Okay. That is about star and Snowflake schema, guys. Okay, thank you.